All right, let's see. Hi, everyone. We're just getting situated here. So I am recording the lecture. I see that a number of you are online. I see 45 of you so far. So we have another 10 minutes before we'll start lecture to allow time for everybody to log in. I've received some chat questions about logging into Carmen OSU. If you haven't already done so, please authenticate. As an OSU student, you are allowed unlimited access to Zoom. So if you're getting anything that says there's a time limit, then you're not logged in through OSU. And I'll announce all of this at the beginning, but as people are trickling in, please sign in if you haven't already done so, carmenzoom.osu.edu. I sent out some of these instructions in the announcements. There are also additional resources on Keep Learning. So please check out those resources if you haven't already done so. And if you get kicked off, then of course this lecture will be recorded, but since there's still time before a lecture, please sign in. And of course, you should only see my video and nobody else's to protect student data privacy. The only thing that will be recorded is, of course, my slides per usual, and also my face, since it is helpful to have a face to a lecture in addition to the voice. So we'll do the best we can to maintain some sort of semblance of continuity, given that this is all moving online right now. All right, let me check. I think I have one chat. Let me see. Okay. All right, so we have, looks like at least one TA. Another TA will be joining us shortly. So your TAs will be facilitating the questions in the chat once we get lecture started. But I'll be announcing this again at 10:20 when we actually start lecture. Okay, hi everybody. It's 10:20, so we are going to get started. Welcome back. This is a different format than what you're all used to. I'm going to start off with just telling everybody what the lecture is going to be like. This was sent out via an announcement through Carmen, so please check that for more details, but I'll summarize it here so that we all start on the same page. So it looks like everything is recording properly and broadcasting properly. So we are going to continue. So if you can see this screen, that means you can see my slides. We've had 3 office hours to confirm this, so I don't anticipate there being any glitches, but we'll see. Okay, I'm going to switch over. So I'll tell you about the format. What was already announced is that everybody's muted, and the only video that is spotlighted is my video. We have Tony Anarino, who's online to help facilitate questions, to aggregate similar questions, and of course, to unmute you all. Given the sheer size of this meeting, it is likely that someone will accidentally hit unmute. And while, I appreciate hearing your pets in the background and such, we're going to try to minimize that as much as possible. Granted, I do have a cat that's roaming around, but she's pretty quiet. Anyway, all right, so we have triple digits now. We have 100 people in the class. Okay, let's see. So yes, Tony as co-host will be able to unmute you if you have a question. Obviously, please submit your questions as we go along, and then I'll try to pause at reasonable times to address all of your questions. The first thing I want to talk about is our response as a class. Now, you have already received a lot of this information in writing through Carmen announcements for this class, but I just want to re-emphasize and discuss it once at the beginning, because obviously some of you have been traveling, a lot of you have been traveling, I anticipate. So in keeping continuity, I just want to emphasize that you should prioritize your health while still keep on learning. We obviously are trying our best to keep continuity. I just want to take a few minutes at the beginning to talk about what will stay the same in the class. As you can tell from the list, that what will stay the same will be a lot, because we're trying to keep continuity and minimize disruption as much as possible, given that we do have to follow new and really rapidly changing university guidelines for a number of things. So just to reemphasize what stays the same, obviously, a lot of you are here during the Zoom lecture, so obviously that stays the same. We're going to try to keep synchronous lecture, but of course I realize a number of you are in different time zones, so we're going to try to work with you on that, given now that we're more global than we were before. The recorded lectures, some of you have reached out to me about this. Everything will be maintained. We'll keep on recording the lectures and posting them for later access. Recitation worksheets are still going to be posted, and recitation we'll try to carry on as much as we can. In the same format, I realize there's a range of tablet access, laptop access, internet access, so we're going to try to do the best we can. And please reach out to us if new issues arise. I know we anticipate issues, but of course, if something comes up that you didn't anticipate, please reach out to us and we'll work with you. Office hours are going to be the same. All the Zoom links are updated on syllabus in the usual Monday to Friday schedule, but now they're just Zoom links so that you can immediately just go, and so you don't have to fish around for these links, and you already know the syllabus page, so we're not going to add yet another thing for you to check. Homework assignment still due on Fridays at 5 p.m. per usual, and of course you have an exam 2 coming up practice exam 2 will be rolled out a week before your review, per usual, in line with exam 1, so that won't be changing. What will change is, of course, we're no longer here in Haggerty Hall, so obviously you're all here, so you know that has changed. We're going to try to do recitation through Zoom breakout rooms, and so your TAs have been practicing this. So we'll see how well that flows, and we may have to adapt and come up with the new solution if that doesn't work out as well as we had hoped. But we'll know when we try it in a larger group, right? A small group testing, it's gone well, but we'll see. And of course, this is also recitation specific. And so what I mean by that is some of your TAs may have other strategies that work just as well. So if that works well, we'll exchange notes, and we may be more uniform in that approach, and we may not, because obviously each TA has their own individual teaching and learning style, just as you do. So any solution we roll out will have been tested, and of course we will optimize it for your learning experience. In terms of flexibility, you've gotten a lot of emails from us, from everybody else, from the university. So we understand that you've had to deal with a lot, and now we're all staying at home. If you're in the state of Ohio or elsewhere, you probably have your own local stay-at-home rules, or at least self-isolation rules. So we understand, and we're trying to be as flexible as we can while maintaining the same set of standards so that we're not changing too much on you. So given that, that is our bottom line. We're trying to be flexible, given everything that you're dealing with, and of course, while still maintaining the same, so there's some semblance of continuity. In terms of checklists, there's a lot of things coming out. So we try to aggregate all of the information in one place. Now, we've been rolling out all information updates through announcements, so please keep on checking that. We also will have started a COVID-19 comm module that basically is the copy and paste of all of my announcements and any other communications. We've had one Carmen message that was sent out. So we're just trying to streamline everything so that you don't have to go to a number of sources to check what is specific about this course as it relates to university guidelines, or even College of Engineering guidelines about pass or no pass. We don't have any information on that because it hasn't passed University Senate yet. So please hold on to those questions for now. I know your undergraduate advisors are being bombarded with these questions because, once again, these guidelines are coming out, in real time. Sometimes we're learning as you are. So we're trying to all just adapt together and stay on top of it so that you're not being just thrown a lot of information and then things get lost in the mix, okay? And of course, we realize if you have a question, as per usual, probably somebody else has a question. So we try to just get the information out there so that everyone has the same access to information through the discussion forum. Now, some of you have reached out to the instructional team privately because it's a personal matter. We understand that, and so we, of course, respect that privacy, and so we'll respond to you in private as well. But any pertinent information that we feel should be shared and could be shared for a more general audience, we will, and we'll repost that, or parts of your question that's deemable for the public on the discussion forum. So please check there. And I know you're getting a lot of links, but I find that this one link is sort of the catch-all. So the Keep Learning website through OSU does summarize all of the how do I access Zoom through an OSU account so I don't get kicked off at the 40-minute mark, because it's not if you sign in as a free account, you may encounter this issue. Now, one-on-one is unlimited, but large group settings like this, it is not unlimited, okay? So let's see, one moment. Okay. And then, of course, software. If you're not already familiar with Carmen Zoom, please just play around. We've had some office hours, and everything seemed to work well. If you're not in that group where you're maybe struggling with the software a little bit, please come to office hours. And of course, ETS and OCIO have office hours for students. I realize it's a lot of ramping up very quickly. So, we're just gonna have to get through this together, but hopefully it'll be somewhat intuitive. And 119 of you are online, so I anticipate that the majority of you will not have this issue. But once again, we realize everybody's an individual, so please reach out if you're really having an issue getting access to the same resources that you've been getting access to. Okay, so here's a good stopping point for any additional questions that I haven't discussed so far, or if you have questions in regards to any of the announcements that have been rolled out, please enter that into the chat and or raise your hand and Tony will unmute you. All right. It appears that there aren't any questions right now. Obviously, you can still continue on and post questions later, but throughout the lecture and of course after the lecture as well. Okay, so with that, let us go over. I wanted to share some information with you because you are part of the class. So I think you should see this PowerPoint now. So this is the result of the Qualtrics. So we're adapting and continuing the online lecture style based on the information that we've received from the Qualtrics. So 94, or at the time, 93 of you had submitted answers. So most of you have found, some place to be. And some of you are looking into housing options. If you haven't already been able to settle this, there is information and resource for you to do so, to coordinate so that you do have a home to go to. And in terms of food, no one has concerns about food, 3 maybe. So if you're still having issues, please contact the instructional team. In terms of internet access, there was one individual that did say that there could be an issue. So, so if you're still having issues, please let us know. There could be a number of solutions that we can look into. So please reach out to us if this is still an issue, okay? And in terms of Carmen Zoom, I think by this time, most of you have already figured it out. So that's good. Something we were concerned about in regards to lecture, asynchronous lecture, and also the exam is, of course, Wi-Fi access and Wi-Fi speed. And it looks like the majority of you will have access to Wi-Fi. In terms of time zones, the majority of you, 88%, are still in the Eastern time zone. I realize there's a distribution of an hour behind, 3 hours, so West Coast time, 6 hours behind, and also 12 hours ahead. So we realize now some of you are in different time zones. So we'll try to post, all the resources such as recorded lectures up as soon as we can. For Proctorio and Carbon quizzes, the minimum speed that you'll need is 56 kbps. So the majority of you have actually access to something faster than that. If you are experiencing some issues, please test it out with the practice exam and let us know, okay? And so that is it for now. It looks like Tony has posted. Yes, so if you have any questions, I'll repeat what Tony just put on the chat. If you have questions, please put them there. So as he is our facilitator for today. Okay, with that, let's continue on with thermal properties. That's chapter 17. Okay. So the objectives for this module is listed here. So are listed here. So there's some terms that we'll introduce, such as heat capacity, specific heat. Let me turn on my laser. One moment, so that you all can see. Okay. Also, we'll discuss the primary mechanism by which thermal energy is assimilated into solids. This is different, potentially different for metal, ceramics, and polymers. We'll talk about linear coefficient of thermal expansion. This is something that you've already seen when we were talking about bond energy curves in module 2. We'll also talk about thermal expansion from an atomic perspective. So what is actually happening and how do we read that off of the bond energy curve or the potential energy versus interatomic bond curve. So we'll revisit that. We'll talk about thermal conductivity, similar to how we've been discussing diffusion or electrical conductivity. We'll also talk about the principal mechanisms of heat conduction in solids and compare it against, the 3 different materials. Of course, this concept, a lot of you have been exposed to because you've taken thermal conductivity in other classes. And of course, and every day, we've all experienced thermal conductivity in, in some way, radiatively, as you see here, through the heat lamp or through the sun. And now we're just going to talk about it from an atomic perspective. What happens when you heat up a solid? Like, what is actually happening between the atoms and also within an atom, and where it sits on the crystallographic site. Okay. So some of the questions, that will come up are, why is it that this specific heat, why is the specific heat, larger for polymers than that of ceramics and metals? What are the determining mechanisms that will eventually result in this property that you observe? Why does the linear coefficient of thermal expansion generally decrease with increasing bond energy? And what are the mechanisms for the energy transfer that's responsible for thermal conductivity? And so you could see here, these 3 parameters are summarized for polymers, ceramics, and metals. And you can see quite a range here for specific heat. Polymers tend to be in the thousands joules per kilogram Kelvin. So you can see here, now it's normalized by the weight. So this is specific heat. Generally, if you're just talking about heat capacity, you're talking about joules per mole Kelvin, right? So now it's normalized by the mass. And so that's what these values are. The coefficient for thermal expansions, you could see the range here, not in the same order as specific heat. You have polymers being the highest, and then metals, and then ceramics. But of course, there's a little bit of overlap. And then thermal conductivity as well. So metals tend to be highly thermally conductive, as you could see here. And so that explains a lot why, if you have a material if you touch a material, right, if you're in an environment where it's, same temperature, let's say you're just in a room, like in a classroom or, in your own home, and you touch something that's metallic versus something that's, made of plastic, the materials feel like they're different temperatures, right? So metals tend to feel colder, but if you have, let's say, a plastic chair and you sit on it, it doesn't feel as cold, right? And clearly these materials are not at different temperatures because you're in the same room, you're in the same environment. So, what is the reason for that? And that's due to thermal conductivity in the material itself. Okay, I see quite a number of chats, so I'm just going to pause here real fast and review if there's any pressing matter. Okay. All right, no specific questions thus far. Well, there are a number of connectivity issues, but we'll get to that later. All right, so let's talk about heat capacity. That's one of the terms that came up first in your learning objectives. So the heat capacity is the ability of a material to absorb heat, right? It's in the terminology itself. It's the energy that is required to produce a unit rise in temperature for 1 mole of material. So we're not talking about specific heat right now. We're talking about heat capacity. So that's related, the heat capacity here for constant pressure is related to the change in energy per mole divided by the DT, the change in temperature. So unit rise in temperature. Okay, so that's the ability of a material to absorb heat. So there are two ways of measuring heat capacity. We can keep the material at constant volume. This is a lot of the case. We can also keep the heat capacity, measure the heat capacity at constant pressure. Obviously, if we're at ambient pressure and we're not confining the volume in the pressure in any way in the measurement in the experiment, that will be at constant pressure. If we're not allowing the material to expand, then of course we're keeping the volume constant. And typically the heat capacity at constant pressure will be less than that of the heat capacity at constant volume. That's something to keep in mind. The trends are similar though for different materials. And so already you see that, here are the units, joules per mole temperature. So here in this case, it's Kelvin, but there are other units such as BTU, pound mole per Fahrenheit. In this class, you may encounter that, but typically, the examples will be done in joules per mole Kelvin. The differences between CP and CV. All right, we have a guest, very entertaining guest, but Euler. Okay, we're back. So the differences in CP and CV are slight for most solid materials at room temperature or less than room temperature. So let's talk about the mechanisms in which energy is stored. So most of the energy is stored as atomic vibrations, and these atomic vibrations can be quantized. So as the temperature increases, the average energy of the atomic vibrations also increase. So what do I mean by that? The amplitude of vibrations increase with temperature, and the atoms in the lattice that vibrate can be described as phonons. So obviously we've dealt with photons before. Those are quantized energy with specific wavelengths. And so when we talk about the vibrations of atoms, here is an example. So you should see the animation on your screen where you can have very low energy. So here you see the atoms sort of vibrate very slowly, low frequency, and then you can increase discretely. And so here, all these atoms, these points that you see here, if you pretend that they're atoms, you can treat them as the interatomic bonding as spring constants. This is something we've dealt with when we were talking about the interatomic, the bond energy curve. So here the energies are quantized. I realize this is just in the lateral position. Obviously in a 3D solid, the atoms can also move instead of just in one direction, they can move in 3D as well. So in the transverse direction. So what you see here, this is a figure from your book, that the normal lattice positions for atoms are in the orange, right? So let's pretend those are, the crystallographic sites. When they're displaced because of the vibrations, that's shown in blue here. So you could see that it's, obviously not on top of the orange atoms anymore. And so we can describe these vibrations as phonons, where we can talk about the amplitudes of the vibrations as well. And of course, they'll change at different temperatures. Intuitively, you could think about the atoms vibrating, and as you increase energy, as you increase temperature, you're putting more energy into the system, you can activate, higher modes of vibrations, or you can activate different phonons. Okay. Okay. All right. So in terms of the dependency of heat capacity on temperature, heat capacity increases with temperature. It is not necessarily constant across all temperatures for a material, but there is a distinguishing line, and that's the Debye temperature. And this it's different for different materials. For most solids, your heat capacity has this A times T cube dependency until it reaches the Debye temperature. And then after that, it limits, it asymptotes to 3R, R being the gas constant. Okay, so this is the plot of the heat capacity at constant volume. And so if you're at a temperature below the Debye temperature, your heat capacity can be calculated with this relationship. And if you're above the Debye temperature, then the heat capacity can be described as 3 times R. Okay. And so we call this the Dulong-Petit limit. So the material is still getting hotter, but the rate of heating is maintained. If you remember, CV is dQ over dt. So the change in heat divided by the change in unit temperature, that rate is now being maintained here, but the material T can still obviously be getting hotter. Okay, it's just the rate is now the same. Okay, let's see. Yep. Okay, so Tony has a few questions aggregated. So I'm going to tackle Tony's question first because he's aggregated some of those questions, and then we'll go down the line and hopefully I'll answer everybody's question. Okay, Tony already responded to everybody. On slide 5 in the equation for K, what is N? If it was mentioned, I missed it. Okay, so let's go back to slide 5. Right. So this is the energy, this is just the energy level. So you can have 1, 2, 3, 4, 5. I realize this is a quantum mechanical approach to this, and your book doesn't go in as great of a detail. So, so you're not held responsible for this, but you are responsible for knowing what a phonon is, which is single quantum of vibrational energy, and how that plays into heat capacity. Okay, as atoms vibrate and be able to your material being able to access to higher vibrational energies, this will feed into the bond energy curve. But I just wanted to introduce it and not just say, you know, here's some phonons, here's some vibrations, you move on. It is actually quantized, and you can calculate all these levels, these different ends. And so you could see here, if you treat this sort of like a discrete levels, you can calculate exactly what the frequencies are and which level you're at. Okay, let's see. Okay, so yes, thank you, Tony, for putting that in the chat. Okay, so let's do an example problem where if we're given for a certain material, let's call it vibranium. Here it has a molar mass of 26.98 grams per mole. Also, I should note in the first upload of the slides, the lecture slides, I had this value as a different value. This has been updated. If you're accessing the slides as of this morning, everything should have been fixed through the box link. If you downloaded the PowerPoint slides before this morning, just please note this value is different and the temperature is different as well. Okay, so I fixed that typo. Okay, so if the heat capacity is given as 0.04112 joules per mole Kelvin at a certain temperature, so 20 Kelvin, and if you know the Debye temperature is 336 Kelvin, what is the specific heat capacity at 2 temperatures, 154 Kelvin, so below the Debye temperature, and 491 Kelvin, which is above the Debye temperature. So let's work that out. So if you have at 54 K, what you're given so far is just the heat capacity at 20 Kelvin. So you need to know at 54K, this is below the Dubai temp. And so we need to know what A is. So we know below the Dubai temperature, this is the relationship between temperature and heat capacity. So we need to know what A is. And so we could do that by using the information that we have. So CV divided by T cubed, and we know at least at 20 Kelvin, okay, this is going to give us A. Okay, so now we figured A because we were given the heat capacity at a certain temperature, and we know that temperature is below the Dubai temperature. So we now know A, we can plug in and calculate CV for at 54K. Which is okay. Thank you. Okay, so that is the heat capacity. What is the specific heat capacity? Well, we know that for vibranium, there's 26.98 grams per mole. So we can say, okay, well, the specific, so now that's small CV. So in your book, there's big CV, capital C, and there's small, lowercase CV. So this is my version of lowercase and uppercase. So specific heat capacity, CV, is just the heat capacity, big CV. Divide, we know that's joules per mole Kelvin, and we know that in one mole for vibranium, there is 26.98 grams, okay? And we know, we talked about before that specific heat capacity is usually joules per kilogram Kelvin. So we'll just put that in the usual notation because we know 1,000 grams is in 1 kilogram. And so that will give us 6.67 joules per kilogram Kelvin. So that is the specific heat capacity for vibranium, okay? Now, for 491 Kelvin, this is above the Dubai temperature. Okay, so the relationship between temperature, heat capacity and temperature is different. It is now asymptoting to 3R. So we'll put that, so now the specific heat capacity is 3R. This is big C. So that's 3 times R being the gas constant. And that gives us 24.9 joules per mole Kelvin. Okay. And little CV, so the specific heat capacity at 491 Kelvin, little CV is going to be 24.9 joules per mole Kelvin. And we know that in 1 mole of vibranium, there is 26.98 grams. And we know that there's 1,000 grams in 1 kilogram. And thus, we get 923 joules per kilogram Kelvin. So that's the specific heat capacity at 491 grams. So I'm going to pause here for questions. Let me take a look. Let's see. What is variable A again? So that is the prefactor in the region below for heat capacity, at prefactor in front of the temperature for heat capacity for a material below its Debye temperature. And what is little CV? So little CV is the notation for specific heat capacity. So now you could see here it's kilograms, big CV, it's per mole. Okay, and so the Debye temperature concept is that at some point as, let's go back. So if you're thinking about these atoms vibrating, right, these having access to these vibronic states, at some point they're vibrating so much that it really, you know, the energy between states is not that different. And so you'll reach some asymptote where it's vibrating like 3R. But for heat, where that distinguishing feature is the Debye temperature, where below that temperature, the spacing in between the quantized energy states are actually quite significant. And you can, we describe that heat capacity relationship as T cubed, whereas beyond or higher than the Debye temperature, it sort of asymptotes. And this goes for all materials for the most part. So for most materials, I should say. I'll correct that. We'll get to the bond energy curves and all these states. I just wanted to note at the beginning that the heat capacity changes as a function of time, as a function of temperature, and it has two different sets of behavior. And that's distinguished between the Debye temperature, where that threshold is the Debye temperature. Okay. All right, so let's look at specific heat for a variety of materials. So already we talked about the different ranges before, but here are some more specific examples and not just, you know, the different classes of materials. So you could see here aluminum, copper, gold, iron, lead, nickel, all these metals. You could see the heat capacities here, ceramics, you know, also quite a range. Polymers, what we talked about before, they have really high specific heat. So that means you have to put more energy in to have that unit rise in temperature. And we'll talk about why that is, because, well, it all has to do with the atomic bonding within these materials, right? It has to do with the number of covalent bonds that are in the system. And of course, polymers have quite a number of van der Waals, you know, secondary type bonding that don't conduct heat as well. Yeah. Okay. So more on heat capacity. We talked about atoms vibrating, but those aren't the only ways that a material will absorb and store that heat. So there is an electronic component. There is also a magnetic component if the material is magnetic. Right? And you sort of saw this in the iron wire demo that was in class, where Janet had come in and set up the wire, and we resistively heated up the wire, and at some point the magnet fell off. It was just attached to the wire, and then it fell off, right? And so there, the magnet fell off at about 770 C, and then there was a phase transformation at 900 C. So the magnet itself is absorbing some heat. So anyway, the kinetic component of your material, it's increased for the free electrons. So, you know, as you know, there are free electrons in materials. Specifically, there are more so in, let's say, conductors, so metals, and they can be promoted to higher energy levels. So we've seen this in electronic properties module, where we talked about electrons going from the valence band to the conduction band. Yeah, and so when you excite these electrons, they can become free carriers and they can move about. So there is a electronic component. There's also a magnetic component where if you have, obviously there are spins, spins if you have free electrons, free unpaired electrons, and you can experience what's called a magnetic transition. And what happens there is that there will be an ordering of the spins, right? So if you have, let's see, something that's not, your spins are randomized, so it's not, it doesn't have a preferred magnetic state. Once you apply a magnetic field, like you see here, right, these randomized spins, if you apply a magnetic field, you can actually align all the spins. And then in that case, you will have some non-zero magnetic state. And so we can make use of these magnetic transitions, and that's what's called the magnetocaloric effect. So here we're tying in magnetism and also heat capacity. I realize the magnetocaloric effect is not discussed in your book, but this is actually quite an exciting area of research in materials that's been around for a while, but it's really coming on board more recently, because it could replace, it could be used in magnetic refrigeration. So, the question, in terms of the application is, will our refrigerators be obsolete in the future, and we can make use of these magnetic transitions, even though right now it's not on the slide, right? I'm saying it's not a dominant way of storing heat, but can it be, right? And so here are some additional slides on just comparing how our conventional refrigerator works. I don't doubt that you all know how a conventional refrigerator works in terms of, a compressor removing heat from the inside of a fridge, it being cooled, outside with condenser coils as the heat goes through and is surrounded by refrigerant to cool it down before it gets pumped back in, right? So that's the conventional way of, obviously, of how our refrigerators work. And, for the most part, they've gotten much better these days and they're quite energy efficient. But can you reduce the amount of refrigerants that are used in these in conventional fridges, right? Can you cut down on these pollutants with magnetic refrigeration? And the answer is maybe. It's obviously it's still quite expensive, but I believe you can buy a magnetocaloric fridge these days, a very small one. Granted, you're going to need a 5 Tesla magnet to align all the spins, but it works in a very similar way. You align the spins. So if this is, your material, you can apply a magnetic field through what's called adiabatic magnetization. So what that means is you just do it really quickly, so that it goes through an adiabatic process, and your temperature will increase. But here you see the spins all align. And then the heat will be expelled during isomagnetic cooling. So the magnetic specimen is then cooled down to ambient temperature under some fields still. And so that's represented by the south and north poles here. And then through adiabatic demagnetization, so you remove that magnetic field very quickly, the temperature will decrease, right? So any heat that you've collected will go away. And then through isomagnetic heating, again, it's heated up in the absence of a magnetic field. So it's very similar to almost like a Carnot cycle, but now you're basically pulling in and out a very high magnetic field. Here it's 5 Tesla. For reference, the Earth's magnetic field is about 30 micro Tesla. So yes, it's a really big magnet. And so the question becomes, how much energy is it going to take for you to power this magnet so that you can have magnetic refrigeration? And does it outweigh all the energy costs of the current refrigerators that we have? But something to think about in terms of heat capacity, being able to store heat, and of course, where magnetism comes in. Now, this is sort of a preview for the next module on magnetism and how all the properties of a material will interplay when you're designing these sort of applications. Okay. All right. So that was sort of an aside. That example was not in your book, but I just thought be neat to discuss something that is being worked on right now in terms of how do we deal with things that get hot, and then how do we remove heat from material. Okay, so here is example 2, more on heat capacity. So let's go back now. So instead of dealing with heat capacity at constant volume, we'll deal with heat capacity at constant pressure. The question is, how much heat must be supplied to 250 grams of tungsten, or W, to raise its temperature from 25 degrees Celsius to 650 degrees Celsius. So this is a really wide range of temperature that you're heating tungsten to, although not that wide, or 650 is actually not that high. And we're given the heat capacity here. It's 0.032 calories per gram Kelvin. So this is the specific heat capacity, as it's per gram. And we need to know how much heat you need. So we're really talking about the Q in the equation, right? And so we know specific heat capacity is the change in the heat normalized by M, the mass that you have, times the change in temperature. Okay, so we want to know what this dq is. And so for this amount of material, 250 grams of tungsten, it is mcp dt. And so we have 250 grams of tungsten, and the CP, the specific heat capacity, is 0.032 calories per gram Kelvin. And the change in temperature is 650 degrees Celsius minus 25, so that is 625. So this is dt, so I can also call it 625K, because we're just talking about the difference, right? And it's just linear, it's plus 273. So the dt is, I can just convert that to K pretty readily. So the units cancel out. And so here we have 5,000 calories. Now, if you had to convert that over to joules, that is just 4.184 joules is in 1 calorie. And so that comes out to 20.920 kilojoules. Okay. Okay. All right, so I'm going to pause here and look at the questions. Let's see. One of the questions is on our slides, why is M not in the denominator? If you downloaded the slides, I didn't catch that typo when I first uploaded the slides. That has been changed for specific, for specific heat, you have to normalize by the mass. This is a conversion. So if you're just talking about heat, right? So 5,000 calories, that's fine. I just converted it to, sorry. I just converted it from joules to calories. It's a conversion. So here it says just how much heat, right? So any conversion factors will be obviously available. So on an exam, you can just, it's open book. So you can, depending on the units that are asked, you can just convert it. Okay. All right, so we're going to go from heat capacity to now thermal expansion. Clearly, materials can expand or change size when the temperature is changed. So for thermal expansion, what we're really talking about is the fractional length that changes and it depends on the linear coefficient of thermal expansion, this alpha L. So we're now obviously talking about 1D, right? Linear coefficient of thermal expansion. For cubic materials, this can be the same, right? Because it's isotropic in 3 directions. If you have a material that isn't cubic, you could have anisotropic thermal expansion. So there you'd have to specify the crystallographic direction that is not like the others, right? So if you have something that's orthorhombic or you have something that's tetragonal, clearly in one direction it's different. So in the tetragonal case, right, A is equal to B, but not equal to the C parameter. So, you know, heat thermal expansion can be different in the C versus in the in A and B. Okay. So, and the linear coefficient of thermal expansion, it is a materials property that indicates the extent to which a material expands upon heating. And so the way we talk about that is we talk about, the way we talk about expansion is we talk about the strain, right? So here we talk about fractional changes. So the final, let me switch back here. The final length minus the initial length normalized by the initial length is related to the linear coefficient of thermal expansion times the change in temperature. So that's the final temperature minus the initial temperature. So we can rewrite all of this as delta L divided by L naught equal to alpha L times delta T. Okay, so graphically we see that here, where if you have some initial length L naught at some T naught, and there's some thermal expansion to LF, where LF is, you know, here in this case, it's longer than L naught and at a higher temperature. And of course, here, the final temperature is greater than that of the initial temperature. But you can also have TF be less than that. In this particular case with thermal expansion, the final temperature is higher than the initial temperature and the material is expanding. I've talked about linear coefficient of thermal expansion. Of course, we can also discuss the volumetric strain. And so that's the difference in the final volume and the initial volume as normalized by the initial volume of the material. And so there, if we assume that the material is cubic, we can think about the volumetric coefficient of thermal expansion as 3 times the linear coefficient of thermal expansion. Okay, so this is obviously a specific approximate case. If it's not, if your material is not isotropic, but if it is, this obviously holds because then your volume is just 3 times that of the linear coefficient of thermal expansion. All right. With the remaining time, I'll introduce the atomic perspective of thermal expansion, and then we'll pick up here next time. So what are we talking about when we talk about expansion? What are the atoms doing? So when we talk about in the elastic regime, the atoms are just vibrating, and that vibration, that elongation of the bond can be recovered. Right? And so we revisit our friend, the potential energy curve, as a function of interatomic distance, or the bond energy curve. So we talked about before that, you know, the bond energy is related to the to this energy E naught here. Okay, and the equilibrium bond distance is R naught. As you increase the temperature, as you put more energy into the system, you can access these vibrational states at different energies, E1, E2, E3, E4, E5 here. And as you remember, if you take the middle of this curve at different energy levels, you'll start to see that the bond distances are being elongated, okay? And that's due to this asymmetry of the curve, okay? And that is related to the linear coefficient of thermal expansion. And so we talked about, you know, the spring model, where if you don't have any asymmetry, your bond length wouldn't really change, right? Because the average at each energy level is going to yield the same R. R1, R2, R3 are all the same. But because there's asymmetry for each specific material here in the bond energy curve, the R values do change. So your material is, expanding, as you can see here. Ceramics tend to look more like this, where there's a lower coefficient of thermal expansion, and so they tend to have a more symmetric energy curve near the energy well. And polymers have higher coefficient of thermal expansion, and that's due to the fact that they have a lot of secondary weak van der Waals bonds. All right, so I've noticed that it is now 11:15 and 27 seconds. So I will stop here, and then we're gonna pick up, review this a little bit, and we'll pick up with thermal expansion at the atomic, with the atomic perspective. All right, with that, this concludes lecture 1 of the Zoom lectures. All right, have a good day, everyone. I'll see you Wednesday.